All right, so we're going to continue in chapter 6. The thing that we're talking about is these equilibrium constant expressions, and this was the last example. The wrong button there. Last example that I did before we did a clicker question. And on this example, I told you that if we had something that involved a pure substance, so this was my supposed to be a solid here. It didn't look like an S very much to find now, but if this were a solid, then A wouldn't appear in an expression. Similar wise, if it's a pure liquid, so if something would have been a pure liquid in the system, so L for liquid, then C wouldn't appear in expression. The only thing that appears, there's things that are in solution, and typically when we think about solution, it's aqueous. We're dealing with aqueous chemistry in this class. Or if it's a gas. Gases count as well because their gas reactions are common types of reactions that occur that we need to think about. So this was our previous clicker question that we answered before we left on Wednesday. And this was a system that was all aqueous. So now I want you to deal with a system that's not all aqueous. See it? Key to working this problem is look at the phases, both reactants and products. All right, take one more. I hadn't voted. There we go. Okay, so everybody agrees that it's answer C. Animation. Now it's set to fly out. There it goes. And indeed, that's the answer. The key thing is that recognize that the phases that involve the solids, those don't appear in the equilibrium constant expression. Gases count the same. For the fact that these are solids, cancel them out of the expression. The gases would count. On this case, both of the products, the things that you have are reactants. So if you think about this over 1, the 1 just doesn't count. Now, if it would have been on the reactant side, you could have 1 over concentration of whatever X or Y was raised to whatever power you need to. Just remember to put the coefficient from the stoichiometry end, raising it to the power. Okay? All right, those are not too tough to do. Just remember what appears and what doesn't. So what do we learn from the K value? Our K value basically tells us what's favored in the system. So we know when equilibrium is established that if we disturb a system, it's going to shift or adjust to a way that it has the least stress on the system. So if we have a system that has a large K value, something much, much greater than 1, then the products are going to be favored. Okay, so there are going to be more moles of products than there is as reactants. That's if you have a large value of K. And we're going to learn that K values vary a lot. We're going to deal with Ks this semester that are 10 to the minus 40th. And we're going to deal with Ks that are 10 to the positive 30th, 40th. And you've got 80 orders of magnitude in between. So K values can reach all extremes in a system, but we need to realize, is that a very large number or a very small number? If it's a large number, it tells us it goes forwards greatly. If it's a small number, it tells us it stays in the reverse direction greatly. So just again down at the bottom, if it's a K much greater than 1, the equilibrium favors the products. If it's K much less than 1, the equilibrium is favors the reactants. I went over this example of Le Chartier's principle in the video. I'm not going to repeat that on you. The thing that we need to be able to understand and predict is what happens with Le Chartier's principle. You might get a relationship question like this. Those up arrows, down arrows. So if you have a system that changes, how does it respond to change? So if we had something that like increase the concentration of a product, so if I have a product concentration go up, the equilibrium is going to respond by shifting back towards the reactant. Okay, so it shifts to the left. If I had a system where I had a change that was a change that increased the concentration of a product, okay, so if I increase the concentration of either A or B, the system responds by shifting to the right in the forward direction. Those are things that we learned in freshman chemistry. We just need to understand that in chemical equilibria, that value for K is not changing. So what's happening is when we establish this value of K, that's concentration of products over reactants, the system responds by changing the concentrations of products and reactants, but K stays the same. Okay, so K it's a constant. It doesn't alter. And keeping that in mind is something that helps you work a lot of problems. That it's the ratio that's going to change to reestablish K. Okay, so in this reaction, this is Le Chartier's principle. So you've got a couple of things that you've got hydrogen sulfide and oxygen in equilibrium with water and sulfur dioxide. And I want to know what's going to happen if you add more hydrogen sulfide to it. How's it going to respond? This should be really easy.
What if it's a solid, but it still shift the equilibrium? I'll ask that afterwards.
Okay, we've all voted. So most people said answer D. So the fact that it's a solid, and if you, going back to your, the way I'd tell you, if you're not sure, always write out the expression for it. So if I write out the K expression for this guy, it's products over reactants. So it'd be the concentration of water squared over the concentration of the hydrogen sulfide squared, concentration of the oxygen cubed. Okay, so miss our thing that's in the on a reactant there. So products over reactants, both products, both reactants. So yeah, which way it's going to respond. So if you increase the concentration of a reactant, it's going to respond by shifting in the forward direction. Okay, so your question was now?
If it's a solid, it just wouldn't be in the K expression. So
That's correct. If this were a solid, and I were to dump more solid into it, what would it do?
nothing.
No change, because that's a solid. So when you have an equilibrium that's involved a heterogeneous system, two phases, and as long as there's any of the solid present and the equilibrium is established, it doesn't matter if you put a spoonful or put a whole jar of more solid in there. It's not going to have any impact on the equilibrium, as long as there's enough solid to establish the equilibrium. Now, when you do solubility equilibrium, we'll talk about in a little bit, you've got to get to a point where you saturate the system before it matters. Because if you put the first couple of grains of the solid in there, it's going to dissolve so the system becomes saturated. What is saturation? It depends on what the value of K is. So for some solutions, you can put up to 50%, 60, and 80% solid by volume in an aqueous solution. Some systems, you can put 10 to the minus 20 grams in your saturated system. It just depends on what solubility is. So it greatly varies. But as long as the equilibrium is established, the presence of additional solid has absolutely no impact on it. So what we want to learn in the next part is, now that we've got these K values, we know how to write equilibrium expressions, we want to figure out how to create new ones. So one of the things we can do is combine two equilibrium constant expressions. So when we do that, we put our K's together. So if we have a K original, all right, that describes the equilibrium of A plus B yields C, and stoichiometry is little a, little b, little c. And if I want to create that into the expression to know what the equilibrium constant value is for K, for the expression where there are two times of that happen, two A's, two B's, two C's formed, the thing I need to do is I would need to have a 2, an additional of these, and I can factor that 2 out. All right, so what it becomes now is that the K original is equal to the K times itself. All right, so the K new is K original times K original, or K original squared. So if I wanted this to be a 5, so if I wanted to write it as this system, what I would do is take K new would be K original to the 5th power, or times itself 5 times. Every time I add it together, I add 1 to it. All right. The other thing we can do when we put these things together is that when we take two equilibriums and we add them together to become a new equilibrium expression, we multiply the values of K. And in this one, I took the reaction, it's a unimolecular reaction. A decomposes to form B, but D decomposes to form C. If I want to know what is the overall expression, I could add those together for the reaction A yields C. If I want to know what's the value for K, the thing that you need to set these up in a way is that you add them together. So if I took A arrow yields B of B, and then B yields C of C. So now when I add the two things together, the B's cancel out. My overall expression is A yields C, but whatever the values for these K's are, so if this is K1, this is K2, the K new is the product of K1, K2. And if I'm going to write the equilibrium constant expressions, I want to think about it that way. If I just took the values for K, K1 is this expression, B over A is raised to the powers, times K2, which is C over B raised to the B and C powers. The B's would cancel out, and my expression is K new is C over A concentrations. Okay, so let's look at putting some more things together. The other one that I don't think I mentioned here, let me throw that on a new page. If I have a reaction, so let's say that I have this equilibrium. All right, so this value is K1, and I want it for the opposite of that. So I have an equilibrium constant expression written for something. It's an equilibrium. It's a two-way arrow always. It's not one way. For A plus 2B yields 3C plus D. Now I know the value of K for this, so I know the value, whatever it is. And if I want to know for the opposite of it, or the reverse of that reaction, what I simply do is now invert the value of K. Okay? That's all there is to it. And so let's put some of these things together and build a few things. So this is the one that was in the notes, but I didn't do it in the calculations because I want to do this in class. So this one is the reaction at the top, two COF2s plus CO2 are yields CO2 plus CF4, and I've got a K value of 2.2 times 10 to the 6. And now I want to find what is the equilibrium constant for the one below. 2 CO2s plus CF2s, 2 CF4s yield 4 CFOs. So the first thing I look at this and I realize is my hint of maybe some type of the rearrangement that I've got to do is I look and see, are the products and reactants on the same side? And first thing I look is the product, or the reactant here is the product on this one. And I look at the other side of the equation. What is the products now becomes the reactants. So I know I've got to invert this. Now if I just do the simple inversion, that takes me part of the way there. So if I take this reaction, the top reaction, and invert it, I get CO2 plus CF4 yields COF2. And now the K for that, K nu, is going to be 1 over 2.2 times 10 to the 6. But that still doesn't quite get me to where I want to be. Because what I need is a 2, and a 2, and a 4. So the way I'd come up with that is I'd take another copy of that same reaction. So now when I add the two things together, I've got 2 COF2s, 2 CF4s, produce the, all right, this should have been 2 and this should have been 2. From that, 4 COF4s, COF2s, and the value for K, nu, which I'm looking for here, is equal to 1 over 2.2 times 10 to the 6, now squared. But I can take my calculator and find out what that is. Okay. I got 2.1 times 10 to the minus 13. All right, any question on that?
C squared, the whole thing.
Say again?
I see.
I squared the, yes. So you, yep. All right, let's do another one. Okay, this one I did in the notes. Here's another one. I gave this as a test question a couple years ago. So you've got a equilibria now that involves copper binding to ammonia. So this is a Lewis acid reaction. You've got lone pairs now being transferred. And it produces the copper, what's the NH3 ion called? I'm sorry, what's the N3 ion called?
Azide.
It's azide, yeah. So azide, so it forms copper azide and gives off hydrogen gas. So I want to know what the K value for this guy is. So this is my goal. But what I have is two equilibrium expressions, and I've got K values for those. I want to see if I can combine those to find out what K at the top is. Okay, so how would I approach this guy? Well, the way I'm going to look at it is find out where are my products and my reactants in these respective K values. So if I look at first, where's the copper? The only place that I find a source of copper in the data that's given is the copper 1+, and it's a product instead of a reactant. And if I look at the next component, is where is the copper azide? I find it's a product in the one I want, but a reactant, so that tells me this one I'm going to have to inverse. So I know I'm going to have to apply an inverse to this one. So that's the first step I'm going to do, is invert that around, see what I need to do. And then the other one that I look at is I find where is the ammonia, and ammonia is on the left on both of these, so hopefully I can use the second one as is. All right, so let's try to put these things together and see what we can do with them. So if I took the first one and if I invert it, Cu plus, what's the azide? Yields copper azide. And now its K value. Okay, so I've spun it around. So that means I need to take the K value and invert it. Right? And now if I took the next one and add to it, what would I get? Well, I'm going to go ahead and write them in the same color. I'm going to write this one as is. All right, so this one's not inverted or anything, so its value just as is. Okay, before I add these two things together, is there anything common to both sides that I might cancel out? The azide ion, top left, bottom right, cancels out of the system. So now if I took those two things and add them together, I get something that matches what I'm looking for. So my K that I'm looking for in my system is just going to be the products of the Ks for these two systems. All right, 4.5 to the third. Okay. Now, I tell you that what makes these somewhat challenging sometimes is that if you get a whole table of Ks. And it's finding out what two things do I put together to create the K for the thing that I don't have. If I give you two Ks, in this case, you know you had to use those two in some way, so you can figure out how to manipulate those. But if I give you 200 equilibrium constant expressions, and you have to figure out which two you need to use, it becomes a little bit more challenging. So you can, and this is really a Gen Chem concept, but we're going to have to apply it throughout the semester a little bit, especially in electrochemistry. We're going to have to rearrange equilibrium expressions to try to predict standard electropotentials. All right, here's what an example of the exam question I had a couple years back. So this is what I expected you to do. So I gave you an equilibrium constant for nickel reacting with carbon monoxide to form the nickel carbon monoxide complex and gave you its value. Now I want to know, taking that piece of information, what is the equilibrium constant expression for the value below? Okay, so if I look at this guy and just make an examination of it, I see that the things that are the reactants are the products on this one, and I see that there's a stoichiometry difference because here it's 1, 4, and 1, and here it's 2, 2, and 8. So my K nu in this case is going to be 1 over the K original squared. So I get 4 times 10 to the 6. Plug in.
So you can only
square the bar value?
Well, there's only one expression here. So if you square the one on top, you're squaring the whole thing, but you got a one on top.
I thought this example, I think it's the same situation with the higher value. With the COF2 going to carbon dioxide and carbon.
Okay, I'm going to go back to it for you. All right. So the same thing here. When we squared this one, we took it to the 1. So you square 1, though, you don't change it.
Oh, yeah.
I got a different answer.
Yeah, I got a different answer too.
Okay, well, I may have plugged in my calculator wrong.
I just raised it to the -2 power.
I don't know. Let me look at my calculator zone, or glasses zone, see if I get the same answer to the 4th. Squared. Oh, no, I didn't. So, oh, I see my typo. Positive 4th, negative 4th. That needs to be a positive. When that becomes a positive, that makes all the difference in the world. How about that? Okay? Exponents make all the difference. 4 times 10 to the -10. Okay? Let's see. Your turn. We're all in here. So we had 2 people choose B. The others chose choice D. All right, so take a look at this. All right, so here we've got our original value for KC. And I've got my reactants and my products, and I see that they've swapped sides. So that tells me I'm going to need to invert this guy somehow. Okay, so just take a look at how we might accomplish it. If I changed it once, if I just invert it, my products become my reactants. So K new is going to be the inverse of that. But now I need it 6 times because I need 6, 6, and 12. So 6 times 6 is 12. I need to take it to the 6th power. And I take it to the 6th power, I get twisty. Okay.
I don't know, I forgot to push on the click. You have 11 responses.
Okay. Did,
Page again. It's an error.
oh, now we have 12. Okay. So, okay. Remember to click.
I did two things, right, because I did that, I thought I was doing that. I guess I don't know that you're the exponent.
That's the thing I encourage you to do is try to do all these calculations. Go over and you can watch the videos in class. Just fast forward to the calculations. Make sure you and your calculator are friends. I just can't say that enough. At least 4 of you on the exam missed a problem where you wrote it out right and your calculator didn't give you the right answer. And I encourage you when you do calculations on the exams to do the calculation twice. You're not time limited. It just takes you a few more seconds to clear it and go through the whole thing again. Make sure you didn't enter something wrong. It's just if you have time, that's a check that can save you points. I'm not going to count the full question off. You're going to get most of the credit for it. If you set it up right, I usually write the word math error next to it, calculator error. But you got to be friends with your calculator. All right. Okay, reaction quotient. So move on to another topic now. The reaction quotient is our way to look at our current conditions. And the way that we do is we take the concentrations at the current status and we compare that to what you would get with the concentrations at equilibrium. So the way that that's accomplished under the current conditions, you calculate the Q value. So this Q is simply a temporary term. We call it the reaction quotient. It's treated exactly the same way as the K expression is. Products over reactants raised to the appropriate powers. You just substitute in the current concentrations. And what we do is we want to compare this value for Q versus the K value. And the thing that tells us is it tells us which way the system needs to go to reach equilibrium. So if Q sub C is greater than K sub C, what happens if this system? That means that there's an excess of products. The reaction has to run in the reverse direction to reach equilibrium. So some of the products are going to decompose back to reactants. Right? If Q sub C equals K sub C, you're there, system's at equilibrium. Right? Now the last case is that if Q sub C is less than K sub C, that means I've got too many moles of reactants. Some of that needs to go to products to make this value come up to be equal to that. So the reaction is going to proceed in the forward direction, left to right. So it's our way to tell us the status of the equilibrium. Is it at equilibrium? Do we have to go in the forward direction? Do we have to go in the reverse direction to reach equilibrium? It's a critical thing we need to understand about how to do a calculation of equilibrium. Are you there? Or which way is it going to have to go to get there? All right. So here's an example of a system that starts with these initial concentrations. You've got dinitrogen tetroxide at a certain concentration and dinitrogen oxide. This is a unimolecular decomposition. So basically, this thing splits in half. Now I've got the K expression. I know the value for K is 4.63 times 10 to the minus third. I need to know, is it at equilibrium or which way would it need to go to approach that? Okay, so let's look at the plugging it in. So the first thing I need to do is just simply calculate Q. What is Q? And it's still calculated exactly the same way. It's products over reactants. So I'm going to put in my values. So the NO2, 1.28. Got to remember to square it. The N2O4 is 0.125. I put my numbers in, 1.28 squared. And I get the value of Q is 13.1. So then I need to do a comparison of K sub C versus Q sub C. Okay, so K sub C is a small number. It's 10 to the minus third. And K sub C is a larger number. It's 10 to the 2. So in our case, what happens is that K sub C, or Q sub C, is much larger than K sub C. Okay, so which way is it going to have to run? Okay, so what it's got to do is it's got to decrease some of this concentration here. And the way to decrease that, to make K sub C smaller, or Q sub C smaller to equal K sub C, it's got to go in the reverse direction. So the equilibrium is going to shift in to the left in this case. And that's simply what we're looking at. Now we're going to learn how to do the calculations to find out how much it would have to shift. We're going to get there and plug in the math for it. And you may remember something in Gen Chem doing ICE tables, but we're going to do a lot of calculations like that as we go forwards. Okay, so here's yours. Well, I saw it cut this off up here. I'm going to resize my page, so let's get that together. So I've got the equilibrium for 2A decomposes to 3B, and I give you the concentrations. And I want to know which is true. So this is that's not clear. That's the value of K. Okay, now I'm looking for 12, not 11. So you can see at the bottom of the page. All in. Let's see. All right, so not as much consensus, but most of you think it's choice C. So let's see if we can figure out why. All right, so I'm going to calculate my Q for products over reactants. So it's going to be the concentration of B cubed over A squared. If you forgot the powers, probably didn't get the right answer. All right, so I've got B is 0.050 cubed divided by the concentration of A, 0.1 squared. Now get comfortable with your Y to the X button on your calculator, how to raise something to a power in a calculation. And I got 1.25. Anybody else get that for Q?
Yeah,
Zero.
0.01 negative 2.
Yeah, I've got 1.25. Let me do it again. Well, I put in 0.01 in mine. Hold on. Okay, so I got this value. Now I need to compare the K value. K is 2.3. Right, so in this case, K is greater than Q. So if we got a case where K is greater than Q, oops, K is, K, Q value, K. Yeah, K is equal to, we said 2.3. So if K is greater than Q, it's the forward direction. So the system is going to proceed in the forward direction so that K is greater than Q. Yeah, so our clicker so it shows us.
That'd be that. Wouldn't that be the third one? Reactance or
Well, it's the one where K is greater than Q. Yeah, so that means it's going to proceed to the right and K is greater than Q. Okay. Not bad. 3/4 of the class gets it. We're getting there. Okay, so in the notes I talk about some more types of equilibrias, and we're going to work specific examples of each of these in great detail. The first of those is the ion product, KW, dissociation product of water. We're going to do lots of solubility expressions. So solubility product expressions, it's where you have a biphase equilibrium, a solid and a saturated solution. We're going to spend the next chapters working on dissociation constants for acids and bases. So Kas and Kbs. We're going to do a little introduction to it here, and then we're going to go forward with it. And then towards the end of the chapter, we're going to talk about complexation formations. So where you have a Lewis acid and a Lewis base react, but most of the calculations are going to be about chapter 16 with this. So we'll get back to those, but we're at least going to introduce them at this point. So let's talk about them kind of in order. This is the table out of your text that lists examples of all of these. We started with the solubility product, and the key thing is that you need to have access to the KSP values. So here's the thing I'll tell you is that you may want to go, if you've got the ebook, you may want to go print those pages out so you can work the problem. Okay, because you're going to need a list of solubility product, the KSP values, the equilibrium constants for solubility equilibriums. You're going to have access to those. So if you got a hard copy text, find out where they're in the appendices in the back of the book. It's not a short table. Okay, that's the thing. You're going to have to learn how to, I want you to learn how to use tables, and you're going to have to go through the Upton tables, and different textbooks organize them differently. Our author's textbook organizes it by ligand, okay, by the different metal or the anions. So they list all the things that are sulfates, and they put them together. And they list all the things that are oxalates and puts them together. And that's this author's way that he does it. Most tables are organized by simple name. So you got to be able to name the inorganic compound, the cation and the anion, and they're put together like that. We're going to have to learn how to use what you have. And I'll post a copy of the table. I'm using a much reduced table from the authors for the test, because the authors you're going to see is 7 or 8 pages long. I'm not going to give you that many. I'm going to condense something down to 1 page. Just remember that now we're talking about a two-phase equilibrium, so the solid's going to be emitted from the expression. Now we're talking about a saturated solution. So the key thing is that as long as you have any excess of the species that's being saturated, it doesn't matter how much is in excess there. And so if we looked at the mercurous chloride cation, and mercury is a unique cation, it forms a dimer. Instead of being a mercury 1 plus cation, mercury reacts together and forms a dimer. But that's mercury. It's a unique metal. Mercurous chloride dissociates into the mercurous cation and 2 chlorines, so products over reactants. The solid doesn't appear in the expression. So if I look at the products, it's the mercurous cation. Take note that because the 2, now I'm not squaring it, it's a single species. Concentration of the chlorine squared, and that's equal to this small value, 1.2 times 10 to the minus 18. That tells me it's a very slightly soluble substance. So I can look at the magnitude of the KSP values, and I can learn something about the solubility in these systems. Now, frequently we relate this to molar solubility, and what molar solubility is referring to is the amount of moles of the original species that dissolves into solution. It doesn't matter if it dissociates at whatever ratio to the cation and anion when it goes into solution. So it doesn't matter if this is a 2 and this is a 4. We're talking about the moles of the original solute that goes in solution. And usually we associate the solubility with an S. And we want to figure out how to relate how much of this substance goes into solution for one of the species that we're going to do the calculation for. Because if I look back at the K expression, this guy doesn't appear anywhere in this expression. So I have to find a stoichiometric relationship between it and one of these species that does go in solution. And I usually want to solve it for the one that's 1-to-1. So I would want to solve this equation for the mercurous 2 plus because it's a 1-to-1 ratio with the species that does go into solution. All right, so it's a 1-to-1 stoichiometry, where this is a 1-to-2. Now, if I found it for the chloride concentration, I would expect we could do that. We can do stoichiometry. That's not a problem, but we just have to figure out how to deal with it. Okay, so we have this generic equation down at the bottom that says molar solubility S is equal to the nth root, where it's the summation of N plus M, whatever these stoichiometries are for the cation and the anion. It's that root of KSP divided by N to the N power times M to the M power. Now this is the generic formula for it. Okay? The next page I've given you maybe a table you had something like in freshman chem. But I just want to show you where these terms are coming out of. So if I had, I'm going to choose a rougher one down at the bottom. So calcium phosphate. The thing that's critical for you is you've got to know your polyatomic ions. And if it's been a long time since you had Gen Chem and looked at the names of the polyatomic ions and figured out how they dissociate, you may want to review those. So if I look at something like the bottom one, the calcium 3 phosphate, to do this, I've got to know the way that it dissociates. So this is a solid. And it's going to dissociate. I know the calcium, based on its position in the periodic table, forms a 2 plus cation. And I know the phosphate is a 3 minus anion. Okay, I can look at the formula and I can see there's 3 calciums here. And I can look at the formula, there's a 2 here and there's a 2 in front of the phosphate. Okay, so if I look at this formula and want to start apply this to figure out where this comes from, this is S, this is 3S, and this is 2S. So if I now think about writing the equilibrium constant expression, the KSP would be the concentration of products, so the concentration of the calcium squared times the concentration, calcium cubed times the concentration of the phosphate ion squared. So I plug that number in, and it would be 3S cubed times 2S squared. So if I take 3S and cube that, So I'd have 27S cubed times 2S times 4S squared. All right, I'm going to go up here and write. Equals 27 times 4 is 108. S cubed. S cubed times S squared is S to the 5th. So that equals KSP. So how do you go from solubility to KSP? I rearrange that. Solubility is equal to KSP divided by 108. It's to the 5th power, so I need to take the 5th root. So that's where that comes from. You just set up the stoichiometric relationship between the anions that dissolve, substitute those things, and remember to raise them to the powers, and solve for it. Now, if you go back and think about it, I'll go back and review this. We're long, and I'll show you how that plugs exactly into that equation as a review to go back into this. But again, you've got to know how things disassociate. So look at the common polyatomic ions from a Gen 2 book. There's about 20 common polyatomic ions. You've got to know how phosphates and acetates and oxalates and all these things fall apart. Okay? You've got to know your formulas. All right, see you in lab segment.
What time we meet?
Well, the last time we tried to go long, we went long, so we'll start at 1 o'clock.